Good afternoon. This is our narrated version of the PowerPoint for Chapter 11, which is all about hurricanes. For our opening slide here, you see a picture of a rather large hurricane. Perhaps that's Katrina. It also could be Rita. Those were both in the same year. I want to say 2005, I believe. So here's an image of Hurricane Igor. Wow, 10 years ago. This was back in 2010. And this one did not hit the Gulf Coast. Okay, so this is really a rather short chapter, but important. Okay, so what do we need to write down here? How about you can skip the middle bullet there. Skip the third bullet, but let's write everything else down. All right, so hurricanes are basically just really big low pressure centers. Okay, so imagine the red L, okay, L for low, red for warm air, but these do not form over continents like our mid-latitude cyclones. These are forming over the oceans, and they're only going to form within a relatively narrow range of latitude north or south of the equator. And of course, these things are going to rotate counterclockwise in the northern hemisphere because they are a cyclone, just like any other cyclone. They're just a lot bigger and they can spread their destruction amongst a lot of people. So they can be rather large, and some of them, if you look at the outer wind fields, they can stretch for hundreds of kilometers across. Now, I am going to ask you to know within what degrees latitude do they form. Okay, so they're going to form between 5 and 20 degrees latitude, and this is north or south of the equator. All right, and why do they not form at the equator or within 5 degrees north or south of the equator? And the answer is a couple of things, really. First of all, the winds are just not very strong right around the equator, and the Coriolis effect. Remember the Coriolis effect and apparent deflection of wind to the right in the northern hemisphere and to the left in the southern hemisphere. The Coriolis effect is pretty much negligible right at the equator. So while we do have, warm tropical seas at the equator that can form thunderstorms, and we can see evidence of that when we're looking at satellite images of the ITCZ, the Intertropical Convergence Zone. These thunderstorms that form right at the equator, they do not come together and coalesce into a hurricane. I'm also going to want you to know what they are referred to in other oceans. So Western Pacific, Southeast Asia, Japan, Taiwan, they're going to refer to them as typhoons. And then, of course, in the Indian Ocean, they are going to refer to them as cyclones. So this goes back to 2008, which is the year I started teaching at UNC Pembroke, 12.5 years ago. Anyway, here we had tropical storms Boris and Christina together. This is a nice map showing where our hurricanes tend to form and in what direction they tend to move. So you see there that indeed right about the equator they do not form. So between about 5 and 20 degrees north or south of the equator. There are a couple of locations that you might otherwise expect hurricanes to form that they just don't, okay? And that's the South Atlantic and the Southeast Pacific. But the South Atlantic, I know of at least one time in the past, say 20 years, that when we have had a tropical storm or hurricane form in the South Atlantic. So it's not impossible, it's just not seen very often. Oh, and then down there at the bottom, I'm sure we'll mention this later in the presentation, but definitely an exam question, probably short answer. When is hurricane season for us in the Atlantic? And the answer is June 1st to November 30th. So it is a full 6 months of the year, and we're not out of the woods yet. Okay, today is what, the 9th? Let me look at my phone. Today is the 8th, and 2020 fall semester, and we're still in hurricane season. And actually right now, as I record this lecture, Hurricane Eta, which is like the 5th or 6th storm this season to use the Greek alphabet, Hurricane Eta has already hit Central America and caused destruction, killed several people. It has moved back into the Caribbean. I believe today it's in the process of hitting Cuba. At this point, it's already, well, it's almost 1 p.m. I think it's leaving Cuba or getting ready to leave Cuba, and it is expected to hit southern Florida. And then we'll see what else it does. By the way, that will tie us for the record of the most named storms in a season. And if we have one more, then we will break the record. And is it possible we could do it? We could. We have 22 days left to go and a warming planet. This is a weather map showing Fran. Okay, so Fran was back in '96. So I moved to Wilmington, North Carolina to go to grad school at UNCW. I moved there back in 2003. I was there for 3 years, getting my master's and working on a research project, and I had an internship with an engineering firm, and I had a fellowship with the National Science Foundation. Anyway, 2003 is when I moved to Wilmington, and those of us that were new grad students, and none of us were from Wilmington, we asked one of the older professors, you know, what was the worst hurricane they had ever been through, and at what point, what category of storm would they leave? And the ones at that point, all of them had been there, you know, in the 90s, and they all mentioned Fran, that Fran was the worst storm that they had been through. And old man Dr. Thayer, he told us that if we were ever going to get hit with a Category 3, he would pack up and leave. So all of us grad students decided that when we saw Dr. Thayer leaving town, that meant we needed to leave town as well. Okay, so again, I'm going to want you to know they're called typhoons in the Western Pacific, cyclones in the Indian Ocean. An interesting fact here, the North Pacific has the greatest number of these storms per year. Okay, so parts of the hurricane, the eye wall. I want you to know that the eye wall is the strongest part of the storm. Okay, so it's basically a big circular wall of cumulonimbus clouds, and you're going to have the greatest wind speed and the heaviest rainfall in the eye wall. It's the worst part of the storm when it hits you. Here you go. So let's take a second and let's write this down. So the eye wall is the most dangerous part of the storm. We'll see on a later slide that the most deadly aspect of a hurricane is going to be the storm surge. And then, of course, it'll be followed by flooding from all the rain. But the eye wall is the most dangerous part of the storm because, again, you're going to have your fastest wind speeds and your heaviest rainfall there in the eye wall. And it'll look like a wall of cumulonimbus clouds. And I'm hoping there's a picture of that coming up soon. And so, question for you, what happens at the eye of the hurricane? And living here in North Carolina, probably most of us know the answer to that question, unless you, say, just moved here from Connecticut or Massachusetts, somewhere like that. Anyway, at the eye, everything is calm. Here we go. So speaking of the eye of the hurricane, your winds die down, and the air will feel pretty much motionless, and the rain is going to stop, and the skies above will clear and will be blue. And it's going to be hot. The air is going to be hot because that air is descending, and then it's heating by compression or heating adiabatically. It's the warmest part of the storm, and there's a good chance that power is out, so your AC is not working. And if you're in the eye of the hurricane, this means that you've already lived through one side of the wall, but you have the other one still to come. So here is a nice cross section of a typical hurricane. And then they're giving us an example of the pressure changes. What else do we might have wind speed as well. Yeah, you see the pressure changes over a few hours. They're on the orange line, and then in the red line, that is your wind speed change. And this is on March 3rd, so I have to wonder, is this which specific hurricane they're discussing here? Actually, that doesn't make any sense to be on March 3rd. I don't know. This slide comes from the textbook authors. It's possible that they accidentally included a graph of a tornado. No, that doesn't make sense because a tornado wouldn't span this many hours. Okay, not sure what's going on there other than it might be a typo as far as the date goes. But what's important here is, actually, let's just leave this one alone. Sorry. Okay, so here's a nice cross section again, a little bit bigger this time. So the eye is a zone of calm at the center of the storm. Again, the air within the eye is sinking and it's warming. So the eye wall, again, your rain and your winds are going to be the most intense. Tropical moisture spiraling inward creates rain bands that pinwheel around the storm center. And that's a really good description on how this happens. And again, if you've ever paid attention on the Weather Channel or your local news outlets as to the dimensions of storms that are getting ready, say, to hit us here in North Carolina, these storms, including the outer rain bands and the wind bands, can be hundreds of kilometers across. Okay, so just kind of a little interesting thing here. Why are the winds fastest in the eye? And this goes to a physics concept, the conservation of angular momentum. So the winds are blowing faster near the center of the storm, which is in the eye wall, and then the winds are not quite as strong on the outer wind bands near the edge. And a good analogy to this is, imagine a figure skater. Say maybe in the, are they Winter Olympics? I'm assuming they're Winter Olympics because there's ice involved. I think gymnastics is the equivalent thing in the summer. Anyway, so your skater can start spinning, and she or he are going to have their arms outstretched. But they can make themselves spin faster without moving their feet. They're not having to kick themselves around on the ice. All they have to do is pull their arms inward and they will spin faster. And this is a good demonstration of conservation of angular momentum. By the way, something I meant to mention on the last slide and forgot, and they were discussing this very recently with Hurricane Eta that is still out there and has already devastated parts of Central America. The meteorologist on the Weather Channel made a reference to eye wall reorganization. Okay, and they said that when a storm undergoes eye wall reorganization, that is something that happens when that storm is gaining strength and likely becoming a higher number on the Saffir-Simpson scale. Not all hurricanes are going to do that, but if they do that, then that again is a sign that that hurricane is growing stronger and therefore more deadly. And here's that same graphic. Doesn't make any sense. March 3rd. Well, I take it back. Let me ask you guys. I wish we were in class together to discuss this. A hurricane on March 3rd. And shame on me for being so ethnocentric to only think about our hemisphere, the northern hemisphere. Remember that when it is winter for us, in the northern hemisphere, it's summer for the folks in the southern hemisphere. So while they're not giving us which named storm this represents, clearly it must be a hurricane that happened in the southern hemisphere. Okay, so I had you write this down before. If you did not, then just make sure to write it down now. Hurricane season, June 1st to November 30th. All right. And of course, that's for the Atlantic. Now, the dates are a little bit different for the Pacific, indeed, and I'm assuming they might be a little bit different for the Indian Ocean. All right, so what fuels a hurricane? What starts them to form? What starts these thunderstorms over tropical oceans to organize and then start to rotate in a counterclockwise fashion? So your hurricanes are fueled by latent heat being released as water vapor is condensing. Okay, so remember how we talked about forming cumulonimbus clouds? So if you have some kind of lifting mechanism and it's warm, moist air like you would expect to find over the tropical oceans, as that air rises, it's going to cool adiabatically as it expands. You're going to hit the dew point temperature. You're going to have condensation, and every condensation droplet that you get is releasing some latent heat energy. So it's going to further warm that air mass so that it can continue to rise higher. And as it rises higher, you'll have more cooling and you'll have more condensation, so you can build these thunderstorms that then become organized and, due to the Coriolis effect, start rotating counterclockwise for us in the northern hemisphere. So, of course, most of them are forming late summer to early fall. So the beginning of hurricane season is June 1st, and that's still spring technically, but it is part of hurricane season. But our busiest times of the year are going to be August, September, and October. So there's kind of a minimum sea surface temperature that you need. You need a minimum of 27 degrees Celsius or higher, providing the necessary heat and moisture to start the lifting mechanism and condensation to begin to build a hurricane. Okay, as areas within tropical disturbances get warmer, several factors help to form hurricanes. So you get a pressure drop there at the surface, creating a region of weak low pressure and cyclonic circulation, which is just referring to a counterclockwise rotation. That is cyclonic circulation, as we would get with any low pressure system or cyclone within the northern hemisphere. So you get higher pressure developing at the top of the storm. Remember, as we discussed with the mid-latitude cyclones, if you have low pressure and convergence down at the surface, you're going to have the opposite at the top, okay? So again, this is just another low pressure center. So higher pressure developing at the top of the storm, causing an outward flow of air from the top. Well, this outward flow of air at the top kind of helps to keep this system going and keep it from breaking down early on. It's basically kind of feeding the low pressure that you get at the center. And we have some numbers listed here in kilometers per hour, but I'm just going to call them out in miles per hour. So at first, it's just simply a tropical depression that may or may not turn into anything. But if your wind speeds reach 39 miles per hour, then it becomes a tropical storm. And at that point, it will be given a name. And if the winds reach 74 miles per hour, then it will become a hurricane. Well, category 1 hurricane. Okay, so when do these things start to break apart? Well, basically you need for them to be cut off from their source of latent heat energy. In other words, they need to be cut off from warm, moist air. All right, so what could happen, say in the Atlantic, let's say it's August, and you have one of these hurricanes to form off the west coast of Africa. Well, they don't all head to the United States. As a matter of fact, a lot of them will be steered closer to Bermuda and kind of just head north into the Atlantic, North Atlantic. So as your hurricane moves over cooler water, it's going to start to fall apart. Or, of course, if it makes landfall. When it's over land, well, then it's not going to, keep growing. It will be cut off from its heat source, its energy source, once it moves over land. Or when you get large-scale flow aloft unfavorable, they will diminish in intensity. Of course, we also know from living in North Carolina that just because they make landfall does not mean they are done. They may stop growing and they may stop getting bigger, but it's already a hurricane or tropical storm, and there's a lot of moisture there and a lot of rainfall and flooding that can happen. And depending on the storm, even some high wind speeds that can happen. By the way, wind shear, let's mention that. So in the previous chapter, chapter 10, which was all about tornadoes, remember that wind shear helps to form tornadoes. So in the case of hurricanes, it's the opposite. If you have wind shear over your tropical oceans, wind shear will inhibit the formation of tropical depressions, tropical storms, and hurricanes. Okay, again, so you're most likely to see them actually develop late summer, perhaps early fall. So again, August, September, and October are usually the most dangerous months for hurricanes. You need a minimum sea surface temperature of 27 degrees Celsius, which is not hard to achieve at least 6 months a year on this planet. And as I mentioned before, why are these not forming right at the equator or within, say, 5 degrees north or south of the equator? And that is because the Coriolis force is very weak. So you're not going to get the cyclonic motion north of the equator or anticyclonic motion south of the equator. And of course, the Coriolis force being so weak near the equator is why the winds tend to be weak near the equator. Remember back in chapter 7, maybe, when we drew the big diagram of the global winds and we talked about the doldrums. Sometimes sailors would experience the doldrums around the equator. And doldrums was not necessarily a state of mind, although we kind of use that term for, when you're feeling melancholy today. But doldrums meaning that the winds were weak and the ships weren't moving around a whole lot. And of course, you need absence of wind shear as well to form these storms. So this is kind of an older little graphic here, but still important. So we're looking at the deadliest hurricanes from 1900 to 2011. You see up there, number 1, you need to write that down. Okay, that's definitely an exam question. So the most deadly hurricane of all, it was only a Category 4, and we might assume that Katrina would top this, but no, Katrina is actually only the third deadliest hurricane to make landfall in the U.S. So back in 1900, there was a Category 4. We weren't naming these yet, so it's just referred to as the Galveston hurricane. So I've seen a documentary about this hurricane on History Channel, maybe. So they think within Galveston proper that they had as many as 6,000 deaths and then another 2,000 estimated beyond Galveston. And of course, you see a little asterisk there, and it says this number may have been as high as 10 to 12,000. They just weren't quite sure. We didn't really have such good record keeping back in the year 1900. And the scariest part about this Galveston hurricane, it wasn't just that it was a 4. I mean, there's many other 4s on this list that kill, less than 500 people. So here's the problem, and I'll ask you guys in a question. Did we have news reporting, TV, radio, Doppler weather radar and really good communication. Did we have any of that in 1900? And the answer is maybe we had radio. I have to admit, I don't know when they came up with radio, but the bottom line here is this. Those people were sitting ducks and they had no idea that this horrible hurricane was coming to them. And Galveston is a barrier island and people didn't evacuate. And so a lot of people were killed. So then the second one there, not on your exam, but this was southeastern Florida back in 1928. So same thing here. We would have had better communication in 1928 than 1900, but still just not enough communication, not able to get the word out. And then, of course, number 3 is Katrina, and we never should have had a death toll that high in 2005, but we did, and that was a failure on so many different fronts. Okay, so this is just to give you an example. This is June 1st. The first day of hurricane season 20 years ago, back in 2010. Okay, so where you go from blue into white and then your orange getting into the red, that's where you hit, where it starts to turn orange, that's where you hit that critical, need at least 27 degrees Celsius sea surface temperature. And you see that you got plenty of that, even way back on the 1st of June, which is your very first day. So, what this slide is showing us is the formation of what they might refer to as a tropical wave. Okay, so this is before you get that rotary motion, that cyclonic motion. So it begins with a tropical disturbance, which is basically a disorganized group of thunderstorms and cumulonimbus clouds. Okay, and sometimes these things will grow a little larger and they'll be linear at first. And they refer to it as a wave, as in look at those blue lines there. And notice that they're kind of peaking in what kind of looks like a wave in the ocean. So that's what they mean by a tropical wave. Sometimes they refer to it as an easterly wave. So, and notice the axis there where it says convergence. Convergence is telling you low pressure, as in the winds are blowing towards the low, blowing towards the center, converging. So that's, and it'll begin in a linear fashion, but then the Coriolis effect will start it rotating counterclockwise, and then that is going to be the beginning of your tropical depression. Okay, are we going to look at this one? We're going to skip this slide. I don't think it has anything on here we didn't say on the last slide. Of course, you're always welcome to pause the recording and take a look at this. And this slide is a repeat, so we'll skip. Okay, here are our cutoffs in numbers. And yes, I think I'm going to want you to know this. No, you don't have to know the wind speeds for the various categories of hurricane, but I am going to want you to know this basic information here. And of course, English, American, British, whatever units, miles per hour. So it'll begin as a tropical disturbance, just meaning that, and what's cool is that the drawing there up at the top, this information comes from NOAA, by the way, National Oceanic and Atmospheric Administration. You see a drawing of a tropical depression, sorry, a tropical disturbance over there on the east, just off of Africa, and then a tropical depression, and you're starting to get a circular feature, then a tropical storm, and then your hurricane. Okay, so it'll begin as a tropical disturbance, just a weakly organized group of thunderstorms. They will form what they refer to as a wave, a tropical wave. And if they keep growing and don't dissipate, then you will start to get that counterclockwise cyclonic rotation. It's a tropical depression once your pressure at the center hits a certain number. And I have to admit that off the top of my head, I don't know what that number is in millibars. And it remains a tropical depression unless the wind speeds hit 39 miles per hour. If the wind speeds hit 39 miles per hour, then it's a tropical storm, then it gets a name. And if the wind speeds hit at least 74 miles an hour, then it's a hurricane. At that point, it's a Category 1. So, clearly this slide is very old. Maybe in the newest version of this textbook, they might have some newer names, but they do agree upon the names, many years in advance. So what's kind of fun about looking at these old ones is to look through and try to see if you can recognize any of these names. Oh golly, there's Matthew, 2016. Yeah, that was a bad one indeed. And I see some names here that have been used more than once, because there was a Hermine and an Ernesto that happened back when I taught at Cape Fear Community College. So that was back before 2008. So clearly these names will get used over and over again. And everybody knows that sometimes names are retired, right? Okay, so, and I might want you to know an example of a retired hurricane name for your last exam. Good examples would be Katrina, Rita, Fran, Andrew, Matthew. Pretty sure Florence is retired. Michael's probably retired. I don't know about Dorian. I don't think Dorian was retired. Mitch. I don't think Mitch is on here because Mitch was further back in time. Mitch is another one that was retired. So there are, Floyd, 1999, devastated North Carolina, coastal North Carolina, well, inland, coastal plain. Anyway, so there are many examples of hurricane names that have been retired. And of course, there will be more retired in the future. So, and something I should have mentioned on the last slide, so we'll just pick it up now. Don't forget that what happens when you run out of names, because for some things some letters they don't use. I don't think they use X or Z because you don't have enough names, so the same ones would keep getting used over and over again. But this season, this is November of 2020, this is the second year since record keeping began that we have had to go into the Greek alphabet. And, in future years, it's going to happen more and more often as our planet warms. Okay, so here are some examples. Oh, there's three of them I had completely forgotten about. Dennis, Katrina, Rita, Stan, Wilma. These are examples, for additional examples for some of them, of storms whose names have been retired. Okay. All right, guys, let's take a look at this image and let's try to figure out if it is rotating clockwise or counterclockwise, okay? So I have to admit that I have to kind of put my hand in front of the screen and kind of move it in both directions to see if I can figure it out. What do you guys think? You think it's clockwise or counterclockwise? Okay, this one appears to be clockwise. Okay, so this is not in the northern hemisphere. This is going to be in the southern hemisphere. We do occasionally get them to form in the South Atlantic, just not that often. And of course, this would not be in September because this is southern hemisphere, so it's going to be in March, which is their summer, part of their hurricane season. Let's get back. I wonder if Andrew is on here. It's not. Okay, so the vast majority of storms on this list of the top 10 deadliest between 1900 and 2011, yeah, Andrew's not on here. And Andrew was way back like in 92 or something. Andrew was a bad one. It really devastated Florida. Okay, so here's your Saffir-Simpson scale. No, you don't have to memorize any of this. But what I want to point out is look at each of these and then look at the wind speed in miles per hour and the storm surge, okay? So write this down now. Hopefully you're paying attention and writing this down because it may not be spelled out on a slide, but the deadliest aspect of the hurricane is the storm surge, all right? So it may be that inland flooding actually kills more people. It just kind of depends on how good a job they did at evacuating people. But the storm surge is the deadliest, all right? And what is storm surge? It's basically a big dome of ocean water that gets pushed up onto the land. And it's just, it can be very deadly. And this is why, you know, barrier islands will be evacuated pretty earlier on, and coastal regions as well. You want to try to get everybody out of the way of storm surge. And I will tell you that this particular hurricane season, on at least a couple of storms that were getting ready to hit the Gulf states, they described the incoming storm surge as, what do they call it? Deadly or unsurvivable, I think is what they refer to it as. And it's good for them to say things like that because they're trying to make the point that you've got to get out of the way of the storm surge. Okay, so even a category 1 is going to have 4 to 5 feet of storm surge. Okay, so look at a category 3, 9 to 12 feet. A category 4, 13 to 18 feet. Category 5, more than 18 feet of storm surge. Imagine your typical barrier island here in North Carolina. Okay, the highest point on your barrier island is probably less than 10 feet. Okay, this is why they tell people that they need to evacuate the barrier islands. And then the wind speeds. The wind speeds are something to be dealt with as well. So your winds are not as fast with your hurricane as they are with your tornado, but there's the hurricanes overall are more deadly because there's so much else going on, including a hurricane making landfall and then stalling and just dumping a ton of rain, like what happened in North Carolina, in Floyd, and in Matthew, and as well in Florence. Okay, and here is that same scale, but showing the pressure in millibars and giving us winds and storm surge in metric units. You will notice I'm going to call your attention over there to the column towards the left where it says central pressure in millibars. Notice that as your scale of hurricane increases, the pressure is going to decrease. It's all tied together. So this is, I'm guessing, gosh, I hate it when they have slides and they don't have any explanation for it. Okay, maybe this is an average over many decades, but there is a story to be told here, and this goes back to something that was on a previous slide that I may or may not have said out loud. Okay, so you're looking at the darker blue tropical depressions, the teal tropical storms, and then as you get into yellow, yellow, orange, darker orange, and red, you're looking at the intensity scale of your hurricane. And then you see the spaghetti string, so that each spaghetti string is a hurricane and the path that it took. So you see that they are incredibly rare in the South Atlantic and incredibly rare in the Southeast Pacific. But I want to call your attention over to Japan and Southeast Asia. Okay, so take a look at their colors. All right, they definitely get more of the 4s and 5s, especially more of the 5s than we do in the United States. Speaking of storm surge, so again, it's a big dome of ocean water, and it can be pretty large, like 40 or 50 miles across. And basically, it's ocean water that gets pushed up onto land. So your storm surge is occurring as your storm is making landfall. And there's a couple of things going on here. So you've got a lot of winds, and the winds are blowing the water up onto the land. And think back to that table that we looked at, and think about how your category 5 can have a storm surge of greater than 18 feet. And that's just crazy. Something that's not mentioned here, but maybe mentioned in your textbook or on another slide, is that part of the problem with the storm surge isn't just the winds and the forward force of the moving storm pushing ocean water up onto the land. It's also the low pressure there. So you've got intense low pressure in the center of that storm. And what it can do is actually cause the surface of the ocean there to rise. Anyway, and of course the bottom line is that you get this deadly, unsurvivable storm surge that moves in when these things make landfall. This is a nice drawing showing in the top graph there, that is somebody's beach house. Maybe it's a hotel, like a single-story hotel. You got your mean sea level. They're showing you where your normal high tide is. So normally your high tide is not touching that structure. And then they're showing you, you know, the storm surge. And the point here is that in these beach areas and barrier islands in particular, like where Galveston sits, is that the storm surge can basically run over top of the island. And of course, the winds can be quite strong and destructive. And you can have missile damage in hurricanes just as you do in tornadoes. Even though your wind speeds are generally lower with your hurricanes than they are with your tornadoes. I'm gonna have to change channel. Oh my goodness, why are they showing them? Anyway, okay. So, but one of the scary things about the tropical storms and hurricanes, and I mentioned this in class and in the narrated PowerPoint for chapter 10, is this. These tropical storms and hurricanes can spawn tornadoes of their own. Now, the good thing about these tornadoes is they tend to be smaller, less strong, and much shorter lived than the tornadoes we get, say, with supercell thunderstorms, squall lines, or dry lines. But still, I mean, the tornado is basically just the icing on the cupcake of doom in your hurricane event. Okay, so, yeah, for a while, Hurricane Floyd was the hurricane to talk about in Coastal Plain, North Carolina. When Floyd made landfall in '99, I forget what month this was, it wasn't that bad at the coast, but then it moved inland, North Carolina, but also up into Virginia. I was living in Virginia Beach at the time. I was going to Old Dominion University in Norfolk, Virginia, studying economics. That was a master's degree that I did not finish because I switched to geology. But anyway, I remember that Portsmouth, Virginia got flooded really bad from Floyd, but North Carolina got hit worse, of course. And, you know, your parents, I'm sure, and grandparents are old enough to remember Floyd and how bad it was. So when Matthew came through in 2016, they were comparing Matthew to Floyd. This is before, okay, not only do you have the, well, I guess C-shaped set of buildings here that are the apartments. I want you to look around this image and you see some houses, beach cottages, you know, scattered throughout as well. And now let's look again at the app. Okay, look at that, guys. There's like nothing standing. Okay, what's left of that hotel? The concrete pad. Okay, I guess that's a swimming pool. Okay, everybody got killed. Nobody that was in that apartment building and stayed, none of them survived. Look at where you had the various houses and beach cottages around. There's really nothing. Looks like a couple of roofs of some kind of structures that for whatever reason appear to be left. Anyway, yeah, so this was a famous hurricane party. The point we're making here with this is if you're ever living on the coast, on the barrier island, or, you know, in a beach town, Wilmington, even if you're not right on the coast, if they tell you to evacuate, that's really what you should do. So this is Ike, and this was 2008, so this was 3 years after Katrina. And this is Crystal Beach, Texas. So we don't have a before image here, but I'm going to ask you, what do you see? Do you see a bunch of flat concrete pads? I do. What do those represent? Those were foundations for these beach houses. And you see there's a handful of them still standing, but a lot of them are not. This is a barrier island. It appears to be a barrier island. This is actually a great shot here, because I just want to point out that have your eyes look, say, from the right, which looks like it's the Atlantic, then moving across to the left, which would be the back barrier side of the barrier island. And do we have any high ground here? No, we don't. Barrier islands are very low elevation and not much above sea level at all, and that's why you got to evacuate. Oh, okay, something here that may not be written down, so I'm just gonna say it and ask you to pay attention and write it down. Take this image of a hurricane and let's imagine drawing two lines on it. Okay, I'm gonna draw a line, say north and south, okay, down the center from the top of the screen down to the bottom, cutting through the eye. And then I'm going to draw another line from east to west through the center of the slide and through the eye. So we're dividing this into 4 pieces or 4 quadrants, okay? So in the northern hemisphere, and particularly on the east coast, the northeast quadrant is the most dangerous, okay? And I know that's an exam question somewhere on your last exam. In other words, you know, which part of the coastline, oh, and do you recognize these coastlines? Okay, oh, never mind, the words are there, they give it away. Anyway, we've got North Carolina, and we've got South Carolina, and we've got Georgia. You know, as bad as it is to have landfall right there where you live and to experience the eye wall, in general, the northeast quadrant is the most dangerous. So they do a little bit of math here. And basically what they're saying is that wind, and this is in kilometers per mile, that's all we got, okay? So your winds are 175 kilometers per hour, and they're pretty equal on the right side of the storm and on the left side of the storm. But the forward movement of the hurricane is at 50 kilometers per hour. Okay, so on the left side of the storm, the southeast quadrant, you can actually subtract those numbers, and your net wind speed there is only 125 kilometers per hour. So we could say that Georgia here is not going to be as hard hit as North Carolina in this particular storm. But go over there to the right where it says net winds 225 miles per hour. Okay, that's your northeast quadrant, as in the top right quadrant. And the problem there is that you have to add together the wind speed of the storm, the rotating storm, and the forward movement of the hurricane. So bottom line here, the northeast quadrant is always the most dangerous. Okay, and if you want to, you can pause the recording and read through this, and they are talking about that as well. Oh, and here we have some English units, okay? So the wind speeds of 175 miles an hour, or sorry, kilometers per hour, are 109 miles per hour, which is very strong. And then you have to add to that 31 miles per hour forward movement of the storm to get the wind speeds in your northeast quadrant here of 140 miles per hour, and that's just devastating. This slide is a repeat. We're going to skip. Okay, this is an interesting slide. This one is not a repeat. We haven't seen it yet. So this is just 2004, okay? So Katrina and Rita are not in here because they had not happened yet. But these are the number of tornadoes spawned by hurricanes and tropical storms in the United States in just one hurricane season, 2004. Okay, so Bonnie, spawned 30 tornadoes. Charlie, 25. Francis, 117. I wish they'd give us, no, they did give us the years. This is 2004. All right, yeah, that was an airhead maneuver. Gaston, only one. Hurricane Ivan, 104. And Hurricane Jean, 16. Okay, and there's a little bit of an explanation down there at the bottom where it's dark green. Okay, winds at the ground level slow down because of friction. All right, the storm has now hit land and there's more topography and more friction. It slows down, while the winds near the top of the storm are not being affected by friction and they're not slowing down. So this gives you wind shear. This is one of the two types of wind shear that we discussed in class last week when we covered chapter 10. This is a drop sonde. Well, a drop sonde is a more general term and can be used in all kinds of atmospheric situations, not necessarily just hurricanes. So this is a drop wind sonde, and this is something that the hurricane hunters can, you know about the hurricane hunters, right? It's Air Force pilots and people from NOAA, National Weather Service, scientists flying into hurricanes on purpose, and they do this very safely. Anyway, this is an instrument that they can drop into the hurricane and get real-time data on things like, you know, wind speed and moisture content, pressure, air pressure, also very important. So we are looking here. This is an interesting little graph. And this just goes, wow, we're going through 108 years here. Not bad. Okay, so first one I'm going to point out is the dark red. That's that devastating Galveston hurricane from 1900. So people did not know it was coming. And look at its path. Okay, it's not like it came across Florida and people in Florida could have sent, you know, telegraph information to, you know, folks west of there warning them. All right, it went through Cuba. Well, it went through the Caribbean islands and it went across Cuba. I think where it is dashed, it was when it was still tropical storm strength. Then it went into the Gulf and became hurricane, and then it hit Galveston and killed between 8,000 and 12,000 people. Camille is on here from 1969. That's in the green. That's from that image we looked at earlier with the Richelieu apartments, and then even though those apartments appear to be made of brick and they appear to be very sturdy, they were just swept off their foundations, I should say. What else do we have? We have Andrew in 92. I'm glad they're showing Andrew. That was quite devastating for Florida. Opal in 95. That one I'm less familiar with. Floyd in 99, which we have mentioned earlier in this presentation. Katrina, of course, devastating and one for the record books, 2008, and then Ike. So it's fair to say that these named storms here, that those names have been retired. They did choose rather large, devastating hurricanes to put on this graphic. Okay, so you're not going to need to know anything about monitoring or tracking. We'll just briefly discuss this. So yes, you know, weather satellites make it more easy for us to monitor and detect the development of tropical storms and hurricanes. However, sometimes the wind speeds, the numbers you get may not be completely accurate. Aircraft reconnaissance. Okay, so these are hurricane hunters flying through and around a hurricane. They will fly through the eye wall and into the eye. Because range is a problem, however, measurements cannot be taken until a hurricane is relatively close to shore. Okay, so that's kind of scary right there, that the hurricane hunters kind of have to wait till that storm is close to who it's going to hit before they can get some accurate data. And at that point, you know, you may not have had everybody that needed to evacuate have them already in the process of doing so. Okay, so radar and data buoys. Buoys, of course, are floating instruments that are out there at sea and are taking real-time measurements of things like the sea level, the air pressure there, temperature. So when the hurricane is relatively close to land, say within 320 kilometers, then it's close enough to be monitored by Doppler weather radar, which is what we use on a daily basis, monitoring our mid-latitude cyclones and anticyclones that come across the United States all the time. And our Doppler radar is measuring wind speed, direction, precipitation. I don't know if they're able to get air pressure from Doppler radar. That's a good question. Okay, so VORTRAC is not necessarily new because these slides are a little bit old, but this would have been new just a few years ago. Vortex Objective Radar Tracking and Circulation, trying to help improve short-term warnings. So constantly monitoring all Doppler radars on the coast and then combining that data to get an overall bigger and better picture of your approaching hurricane. Okay, so data buoys are in fixed locations along the Gulf and Atlantic coast of the United States. And of course, these things might occasionally stop working or get destroyed by a storm that comes through, but we have plenty of these things out there constantly monitoring what's going on in our oceans, trying to get a look at where we might have a tropical disturbance form. Hurricane watches and warnings. I think this is an extra credit question. Yeah, I'm pretty sure it's extra credit. Okay, almost nobody ever gets it right, and that's okay. So this is a little different from the tornado watch and tornado warning, all right? By the time you have a hurricane watch, even just the watch, it's out there. It's formed. We know it's there. We're monitoring it. We're tracking it. They will issue the watch 48 hours before the tropical storm force winds will hit your area. And the winds are going to hit probably before the rain bands or maybe along with the rain bands, but they will hit certainly before the eye wall does. And of course, the idea is that when you're in an area under a hurricane watch, if that's above a category 1, they're probably going to be asking everybody to go ahead and start evacuating. So they'll change it from watch to warning when it's 36 hours away from the onset of the tropical storm force winds. Something that isn't mentioned in this PowerPoint, but I'm going to talk about it, is rip current risks, okay? So all of these storms, tropical storms, hurricanes, whatever number they are going to cause an increased risk for rip currents. And even if these things are not going to make landfall at all, if we have a hurricane out there that's getting steered towards Bermuda, it's still close enough to the East Coast that they will start calling for an increased risk for rip currents. All right, so just a quick lesson on rip currents. All right, can you see them from the shoreline? Not necessarily. They tend to form in between sandbars. Sometimes, if you do a Google image search, you're going to find images and you'll get an idea of what it could look like if you're lucky enough to be able to see that rip current from the shore, but you can't always tell that it's there. And I hope you guys know what to do if you're caught in a rip current, and if you don't, this is what they tell us. So you're swimming in the ocean, your friends are sitting on the beach, you're out there, by yourself, and you feel yourself being pulled out to sea. You notice that you're getting into deeper and deeper water fast. Okay, the thing to do is to swim parallel to the shore. So you swim north or you swim south, and you do that until you feel like you're no longer being pulled away from shore, and then you can try to make your way back into shore. If you panic and just start swimming with all your might directly back to the shore, chances are you're going to get tired and you're going to drown. Okay, because Even Michael Phelps is no match for a rip current. So just keep that in mind. If you ever are caught in a rip current, don't panic. You want to calmly swim either north or south, parallel. You don't have to swim that far, maybe 300 feet or something like that. That'll, north or south, parallel to the shoreline, that'll get you out of the rip current, and then you can make your way back to the shore. Okay, this is Tropical Storm Dean back in 2007. I don't even remember that one. It must have not been all that big a deal for us here in the United States. But this is a neat little graphic just showing, how they might track this. Okay, so yeah, the Galveston hurricane in 1900. So again, anywhere from 8,000 to 12,000 people total were killed, and you will have an exam question where I'm going to ask you, what was the deadliest hurricane to hit the United States? And it was the Galveston hurricane in 1900. That's what its name is. We weren't naming them then. It's just known as the Galveston hurricane. And look at the destruction. I mean, just gosh. Again, it kind of looks like a tsunami hit. So notice the NOAA emblem there on that jet. Okay, so these are your hurricane hunters. I have to admit, I think this would be a really fun job. I don't even like getting on an airplane. I'm scared to fly, but I would love to go work for these people. Besides, I think they have really good pilots because they're, Air Force pilots. I guess they could be Navy pilots. And then here is an image of, gosh, who knows? Could be Katrina, could be Rita. But, an image like this showing, the different states in the Yucatan Peninsula there, where Cancun and Cozumel are, it gives you an idea of the enormous size of these storms. And when you can see a well-defined eye, like we see with this hurricane here, that's a sign that it's a very powerful and strong storm when it has a well-defined eye. And here is that same storm? It could be a different one. Here, what you're looking at, and this is one of our GOES satellites. I wonder which GOES this was. Oh, this is August 29th, back in 2005. Could this be? This is either Katrina or Rita. I can't remember what particular day in August Katrina hit. But anyway, this is one of our older versions of our fancy weather satellites, the data that you get from it. And of course, as you get there into the warmer colors, you're looking at stronger winds and more intense precipitation. And of course, you got a well-defined eye. Here you are looking at wind speeds. Okay, and can you find the eye of the storm? I think you can. Look kind of in the center there of the purple. All right, so your faster winds are there where it's purple. And looking at those wind flags, you definitely are reminded that these hurricanes are going to rotate counterclockwise in the northern hemisphere. Okay, so these are our symbols. Okay, so if it's a tropical depression, it is an open circle. If it's a tropical storm, it's that thing there in the middle. If it's a hurricane, it's the one there on the bottom left. So the difference between the tropical storm symbol and the hurricane symbol is that the hurricane, it's filled in the center and it's open in the center for the tropical storm. And here, this is another radar image, and in this case, they're looking at rainfall. And as you get into the warmer colors there, you're getting higher rainfall rates, including 12.8 inches, which is enough rain to flood anywhere, really. Here's an image from one of the data buoys out in the Gulf of Mexico. Hurricane Kate. Gosh, that was a long time ago, 1985. I don't remember that one. But, oh my God, guys, look at the date, November 20th to 21st, 1985. That's crazy. So yet again, I'm going to point out that this Hurricane season we're in right now, 2020, which has been a crazy year in so many ways. Anyway, we're only on November 8th, and we've already tied for the record number of storms. Could we have another storm? I think we could. I would be surprised if we don't break that record. Anyway, this is proof it can happen. This is Hurricane Kate, almost to the end of November. Okay, this slide is a repeat. This slide is a repeat. This is kind of a neat little graphic here. We're almost done with this, by the way, I promise. Let's kind of divide this up into half. Let's choose 1922 and say that's half of our data, okay? So looking at the left side of that, 1850 to 1922, category 4 is in blue. Gosh, hang on, guys. I got to figure out how. Okay, how to read this. Okay, in red you have the total number of storms, okay? In blue you have storms, I guess the total number that are category 4 or 5. In black they're just kind of averaging a 10-year average. All right, so yet again, let's choose 1922 and just say that's the middle of our data. So from 1850 to 1922, compare the number of category 4 storms, or the number of storms in general, to what you see on the right side, which is from 1922 to 2006. Okay, so it does appear that our storms are happening, and this is old data. This would be even more obvious to us if we had a more recent one of these, say at the end of our hurricane season for 2020. It does appear that our total number of storms are increasing over what they had been in previous decades, and the total number per year of category 4 and higher storms are increasing. And the intensity of these storms is increasing, and they tend to make landfall and often stall and bring about catastrophic flooding. And here we have some silly cartoons. This slide actually comes from Dr. Edgell. I borrowed some material from him when I first started teaching this class. This might be the last slide. Nope. This might be our last slide. I kind of like the one on the left there. The latest way to deal with tropical depressions. Throw a bunch of Prozac in there. Okay. Anyway. Oh my goodness, this is a cyclone that hit Myanmar back in 2008. This was quite devastating. Hey, this is South Africa and Zimbabwe. All right, so, okay guys, what hemisphere is this? You can tell either from trying to figure out the rotation of the storm or from the fact that we're looking at South Africa and Zimbabwe. Do you guys get it? This is Southern Hemisphere. Whatever name the storm has, if it has a name, they're not giving it to us. But anyway, they do deal occasionally with the rare hurricane there in the South Atlantic. Oh, this is actually kind of a good question here. So this was the track of Hurricane Gaston. I forget what year that was. Anyway, should the city of Houston expect to experience Gaston's fastest winds and greatest storm surge? Why or why not? All right, remember dividing your hurricane into 4 quadrants, okay? And remember that the northeast quadrant is the worst. So Houston, while they are close to where the eye wall is going to make landfall, they're on the southwest quadrant, so things are not going to be as bad for them. They won't experience the worst winds or the greatest storm surge. But look at that hurricane heading to Dallas. Okay, what is the greatest threat to life and property if the storm approaches Dallas? You guys got it? Yep, rainfall. Because once these things hit land, they tend to slow down. Yeah, probably going to have a lot of flooding there in Dallas from that storm. I'm sure they did. This is Rita back in 2005. This was after Katrina, maybe around a month or so after Katrina. Okay. All right, we have two lines here. We have A and we have B, and then it shows us where it makes landfall. Okay, so questions. Which line represents air pressure and which line represents wind speed, and how did you figure this out? What do you think, guys? A or B, which one is air pressure? Do you remember that hurricanes are low pressure centers, right? So A has to be pressure because it's dipping down there. And then the one that appears to be almost a mirror image is line B, and that's going to be the wind speed. Remember, as your air pressure drops, your wind speeds are going to increase. Tornadoes and hurricanes, how are they alike? How are they different? So many things we could say about this. We're going to let it go. This might be our last slide.